Hey, we're going to talk about diskless Kafka today. Happy April Fools, it's April 1st, and we're going to be reading this article by StreamNative called We're a Kafka Company 2. Now, initially, I thought this was an April Fool's joke because these guys are a poster company, but it seems like it's actually not a joke, and it turned out to be a very interesting article. So I have a couple of things I want to touch on around diskless Kafka today and the ecosystem and the protocol and etc. So let's just get into it. Let me say something that might surprise you. We are a Kafka company too. Yes, us, StreamNative, founded by the creators of Apache Pulsar, the Pulsar company, the not Kafka company. And no, this isn't an April Fool's joke, although the timing is inconvenient. These guys were the Pulsar company, in case you didn't know. StreamNative was the Pulsar company. I opened up a Crunchbase here. It says StreamNative offers a streaming platform based on Apache Pulsar that enables companies to access enterprise data as real-time streams. And Apache Pulsar was literally just a Kafka. In a way, a better Kafka because it had split the compute and storage. It had done the compute and storage architectural separation way earlier than Kafka. In a way, I always compartmentalized Pulsar in my mind as rebuilding Kafka after you've noticed what sort of mistakes Kafka made. I think Pulsar was created a few years later than Kafka, so it had the ability to do some things better than Kafka because it basically learned from the troubles. They have some wonky fancy graphs here that kind of show you how basically you have a broker, which is the Pulsar broker, and the storage is actually done by a thing called Apache Bookkeeper, which has its own brokers called bookies, and they replicate the lock between each other. And I think there was a zookeeper used between these two systems. To be honest, I haven't really tracked how the company or the project has evolved. But from what I remember, it was basically a more feature-rich Kafka, although also a more immature Kafka because it's generally used a lot less than Kafka and doesn't have as big of an ecosystem. But you can see some of the features here. But anyway, these guys were a Pulsar company, and now they're also a Kafka company too, it seems. The truth is, we've been on a journey that none of us fully anticipated when we started. That journey has gifted us a lot of experience that helped form the following conviction. We should operate a native Kafka service. Interesting. What in 2019 may have sounded to us like defeat, offering a competitor system as a first-class product, no longer holds true. In 2026, the majority of engineers no longer define Kafka as a system, they define it as a protocol. That is very correct. I was actually talking to Justin Manchester, we were discussing the IBM acquisition a few days ago on a podcast here on this same channel, and he said that Kafka is the protocol and Kafka is like the TCP IP to your data layer. And I agree very much with that statement, and it's really interesting to see these guys say the same thing here. You actually see that they mentioned TCP IP as well. They must have got that from the interview. But it is true that after all these implementations that we've seen in Kafka land, like the diskless topics and WarpStream and the Confluent stuff and RedPanda and yada yada, Kafka really is being defined as a protocol because we have more systems, like we have probably 10 systems that implement the protocol, and at some point you have to ask yourself, when you say Kafka, are you actually talking about the open source project, or are you talking about the protocol? The protocol is governed by the open source project, but then again, chances are you might just be using one of these other 10 systems rather than the open source thing. So in a way, we really are in an age where the protocol is everything, and Kafka as a system is just one of those systems, even if it's the open source one, and even if it is the system that created the protocol and etc. But yeah. Supporting another protocol seamlessly is an expression of a platform's strength. Let me explain. The power of open protocols. There's a pattern in data infrastructure that's worth understanding before we tell our story. When you integrate with an open protocol or format, you inherit an entire ecosystem overnight. Consider what happened with open table formats. When Apache Iceberg and Delta Lake emerged as open standards for lakehouse storage, something remarkable followed. Any system that wrote data in these formats, regardless of who built it, instantly became queryable from Snowflake, Databricks, Spark, Trino, and dozens of other analytics engines that are growing by the day. No partnerships were required, no custom connectors were required, the format was the integration itself. That's a very good point, and there's a big powerful point around, I think I would call it standards, really, open protocols or just standards. When you figure out a standard and you attach yourself to that standard, everything sort of follows naturally. I've heard similar examples of, back in the day, even railroad tracks, how your train runs. I think I might be, don't quote me on this, but I'm very sure the whole world, or a majority of the world, has standardized on particular sizing of railroad tracks. I think every railroad in the world is more or less the same size. Similarly, cars are very similar sizes. There are multiple electricity standards, for example, but point being is that when you standardize on one concrete solution, you get this network effect built up where, if I'm a railroad track producer and I produce some railroad tracks for the USA, let's say, I can actually sell it to China, I can sell it to Europe, I can sell it to South America, I can sell it to the whole world because everybody else actually uses the same thing. So in a way, every actor in the system is incentivized to adopt the open standard, because they gain a lot from it as well. And that's a big thing here, and I think that's what they're sort of explaining here, which is, if you, for example, support Apache Iceberg and you store data in Apache Iceberg, suddenly you have almost a first-class integration with all of these other systems that have also chosen to integrate with Apache Iceberg for perhaps completely different reasons. But it's really interesting how the game theory around, what protocol do you support and what do you integrate with plays out. And I think they're going to say the same thing here about Kafka, which is, once you integrate with the Kafka protocol, suddenly Kafka Connect works, Kafka Streams works, Flink works. All the little tools that help monitor Kafka or write messages to Kafka, Spring Kafka works. All of these, auxiliary stuff that were not made, let's say, for Apache Pulsar, or were not made for the StreamNative product, or were not made for whatever, RedPanda product, they suddenly work. And that's a big thing. You're getting the ecosystem for free. So they say here, the format was the integration. We experienced this firsthand ourselves. When our storage engine, Ursa, began writing directly to Iceberg and Delta Lake formats and object storage, we did not need to build connectors to every analytical platform. Our streaming data was simply there, immediately discoverable and queryable from any engine that reads open table formats. The open format did the work for us. That's true. They could have also used Connect because they have, I think they had the Connect, they had the Kafka API before this announcement too. To some extent, they were supporting it. But yeah, even with the open formats, they do the integration. The same principle applies to streaming protocols and every other protocol, I would say. The Kafka Wire protocol has become the lingua franca of data streaming, not just because of Apache Kafka itself, but because of the dozens of systems collectively that made the protocol ubiquitous. Every cloud service, every vendor, every connector, every monitoring tool, every tutorial speaks Kafka. The protocol has become the TCP/IP of streaming. This is the quote I was looking at. But it really has become the TCP/IP of streaming. When you attach yourself to an open protocol, your product benefits automatically. That insight, validated by our experience with Lakehouse formats and now with the Kafka protocol, is the thread that runs through everything we're about to share. How we got here. We started StreamNative a few years ago with Apache Pulsar, a system we built at Yahoo to handle the massive scale of unified messaging and data streaming. Pulsar had the right architecture from the start, the compute storage separation, multi-tenancy, and multi-protocol support. It was designed for the cloud before cloud native was a buzzword. And enterprises loved it. They deployed Pulsar for their most mission-critical workloads, the ones where downtime isn't an option, data loss is unthinkable. But along the way, we noticed a pattern, a very consistent pattern. Most of the world lives in a split world. Organizations run their mission-critical messaging and queuing workloads on Pulsar and their data streaming pipelines on Kafka. For better or for worse, the Kafka protocol had become the default, not because Kafka was architecturally superior for those use cases, but because the sheer weight of ecosystem adoption made it the path of least resistance. That's a good point. Every vendor, every tool, every connector, and every tutorial, again, Kafka. And that is a good point. We've had other examples from the past in technology. I think even the VHS versus whatever its competitor was, I think it was something by Sony. Let me see if I can pull it up. VHS versus Betamax. Why did VHS win? I think this was the thing where they had the format wars back in the 70s and 80s. Obviously, I was not alive for that. But from what I've heard is that Betamax was actually a better product and a better format than VHS, but nevertheless, VHS is the one that won out for whatever reason we're not going to go into here. So it's just an example from history that it's not always the better thing that works. there's a lot of path dependence that wins. There's not always the better thing that wins. There's a lot of path dependence in these things. Who releases it first? Who gets more traction amongst a higher amount of people? And then the network effect starts spinning, and one person wins. So I think it makes sense why Kafka won here. It was first, and it's the one that basically coined the lock and this sort of data streaming paradigm. So I would have been surprised if Pulsar won there. Okay, we have a long history of making StreamNative Kafka friendly and are no strangers to the API. I think they mean the Kafka API here. In 2020, we released Kafka on Pulsar, an open source protocol handler that let Pulsar brokers speak the Kafka wire protocol. At the time, we weren't conceding anything. We were hedging our bets, meeting users where they were. Then came KSN, Kafka on StreamNative, a more deeply integrated production-grade Kafka compatibility layer. Each iteration brought us closer to full Kafka compatibility. Customers could bring their Kafka workloads to our platform without changing a line of code. Okay, so they did have history with that. I even have a memory that it was earlier than 2020, but who knows? But I guess some of these learnings they already had in 2020, and they were already seeing who was sort of winning the ecosystem. I guess they just wanted to play a war on both fronts, build the superior product in their eyes and build a superior protocol, but also support the old one. Because even if you're on Kafka and you want to migrate to Pulsar, that migration is a lot of work. Having to change so many clients, potentially hundreds of clients, that's essentially opening Jira tickets for every team that has a Kafka client and saying, hey, forget this API that you know and understand and change your client to work with this new Pulsar API who even knows if it's supported in your language, in C, in Rust, in Python, etc. So even back then, that strategy, I think, made sense for them because if you're targeting Kafka customers and giving them a Kafka API is a really good way to migrate, because you basically tell them, don't even change your clients, we'll just give you the backend, which is Pulsar in this case, but you still use your Kafka client. And when you have time or when you have desire, you can move your clients, or maybe you can just move your new clients, etc. I think that was a very smart move of them. And I'm kind of surprised we haven't seen more of these things, of multi-protocol support where the backend is, let's say, Kafka. Like, for example, why can't there be, let's say, a Kinesis client that actually writes to Kafka? Or not a client, let's say a proxy or a Kafka protocol handler or whatever, that lets you save the data to a Kafka but gives you, let's say, the Kinesis API in case you have a lot of clients using Kinesis. But I'm digressing a lot here, so sorry. Okay, over time the picture became clear. It wasn't that Kafka the system beat Pulsar, it was that Kafka the protocol had won. Propelled not by Confluent nor the open source project alone, but by dozens of Kafka compatible systems that collectively made the wire protocol the industry standard. I agree with that. I think Confluent had a lot to do with it, maybe 80%, but certainly all the other people working on top of Kafka and that API helped. And then we built Ursa, a Lakehouse native streaming storage engine, so it's an engine, that writes directly to object storage in open formats like Iceberg and Delta Lake. The engine did not require local disk, did not require leader elections, and did not incur any cross-AZ replication costs. It happened to be really, really good at running Kafka workloads, up to 95% cheaper, in fact. Good enough to win the VODB 2025 Best Industry Paper Award, beating submissions from Databricks, Meta, Alibaba, and many others. I need to read that paper, by the way. It's a good paper. I skimmed it once. I think it went over all the stuff they've done. So Ursa is, again, a diskless type of thing where it writes directly to S3, and that's why they say it's up to 95% cheaper. I guess if you're running open source, because if you're buying it from a company, then there are other costs to pay there. And in any sort of Kafka project, as I've said multiple times, the cross-AZ replication costs are really the majority of the cost. I can run a live calculator even to check it out, but if you go like, let's say 500 megabytes a second of producing 1 gigabyte and you run it, you can see that your yearly cost for running a Kafka is 2 million, of which 115K is your monthly networking cost. So if we run that times 12, you would get 1.4 million a year you would pay in networking cost in a Kafka that takes 500 megabytes a second in and 1 gigabyte out. That's extremely expensive. Now imagine if we go to gigabytes a second. That's more than 50% of the total cost. So that's how these diskless architectures save so much money. That's why they can say they're up to 95% cheaper, because they not only eliminate the network cost, this goes to zero, literally, in these systems, but also the storage cost goes a lot lower as well. And counterintuitively, also the instance cost goes lower as well, because you have less instances or less CPU spent replicating between the brokers. You get that replication for free in S3. But again, digressing here. And then we did something nobody expected, including us, introducing Ursa for Kafka. We took Apache Kafka 4.2, extended its storage layer with Ursa, and built a native Kafka service called Ursa for Kafka, UFK. It's not Kafka compatible, or it's not Kafka on something, it's native Kafka, with its classic storage engine and with an additional lakehouse engine underneath. And they have this very good visualization here, which I liked and made everything very clear. So from what I understand is they've just added a separate write path to Kafka, backed by a separate storage engine, which is their proprietary Ursa storage engine. And here you can use Kafka as normal. It's a Kafka fork. It's the same Kafka code base with additional code that somehow routes the stuff to the Ursa storage engine. The classic write path goes the same as Kafka does. It goes to your, to your local disk on the broker. It replicates it to the other two brokers, and they use their ISR replication protocol, and then they respond, and that's how consuming and producing works. But with the disk listing, I guess it goes to the Ursa storage API, and then whatever happens behind the scenes, we don't necessarily care, because that's the Ursa storage engine's problem. But most likely it writes to S3 directly in some form of batching. There'll probably be higher latency here. And at some point, I guess, it compacts it into a so-called lakehouse table, which is just to say it stores the data from the Kafka format, from the Kafka message storage format, to a open table format, which is probably Iceberg or Delta Lake, backed by most likely a Parquet file, really. And it's column-based as well. So I'm curious how this conversion happens here and how the performance is for reads. I think reads are a little bit more difficult when you're reading these lakehouse tables. And they didn't say too much here about the type of topics that they support and the type of workloads they're aiming with this, but I think, we'll get into it. So why build a native Kafka in the first place? A natural question. Why build directly on the Kafka code base instead of continuing to build protocol-compatible systems on top of different storage engines? This is a good point. Before this, they had Apache Pulsar, which is a separate code, completely separate project, separate code, which I guess they still have. But now I think they're introducing another product where they've taken the Apache Kafka code and extended it a little bit to share this Ursa storage engine that they used from their proprietary Pulsar product as well. So I guess they have two products now. And the question is, why build a native Kafka instead of continuing to build on their proprietary or open source Pulsar product? They say because we tried that and learned exactly why it doesn't work long term. We spent years building Kafka protocol compatibility layers. Each generation got closer, but we kept hitting the same fundamental problem. The Kafka wire protocol is not just a specification, it's a living system with undocumented behaviors, implicit client-broker contracts, and edge cases that no spec captures. Kafka has 89 live request families today, and when you account for backwards compatible versions, you're looking at hundreds of protocol permutations to implement and maintain. That's actually a really good point. So Kafka does have a lot of requests that it handles. Let's say 89 here, I'll take their word for it. And when you account for all the different versions, because as Kafka releases new versions, let's say the produce API has version 1 of the request. Then a new Kafka version release, and maybe they change something in the produce API, it goes to version 2. I think it's up to version 10 or 11 today, something like that. So when you account for all of those, 89 times 10 or whatever, I can see how you're looking at hundreds of different request versions that you need to support, and that definitely becomes tricky to do. So as I say, every time upstream Kafka evolved, we had to catch up. And every new version meant new surprises hiding in the gaps between what the protocol says and what clients actually expect. I'm not sure if there are that many gaps here, as they say. So I'll mark this as orange-yellow or orange-red. But there definitely could be some gaps. And I think I've seen bugs that do show some gaps. It's normal, obviously. I mean, it's a complex system with a lot of, with hundreds of request versions to support. So there could be some stuff that don't really align. Another thing I saw a lot, I think systems like this that re-implement the protocol hit is client implementations can be different. We have the official Java client, which is sort of the spec, what people copy. Then we have the Apache Kafka, which is another thing that writes on C. And then we have a lot of other clients that also implement the protocol in their own way. So it's also easy for these clients to have like different understandings of how something should be done, and then things can break. We'll share the full catalog of war stories in an upcoming post, but the lesson wasn't ambiguous. Re-implementing the Kafka protocol is a treadmill with no finish line. Wow, I like that. It is a treadmill with no finish line. Every sort of protocol is. Building directly on native Apache Kafka changes the equation entirely. UFK inherits, Ursa for Kafka inherits perfect protocol compatibility by simply using the same code. When upstream Kafka introduces new APIs, changes behaviors, or fixes a bug, we inherit it for free. That makes sense, right? Because they're using the same code. It's literally just Kafka. This is literally just the Kafka code base they're using here. So when Kafka releases a new version, they just run git rebase and fix the merge conflicts or whatever, and then they have all the fixes. So that's really cool. That's something that some other systems like RedPanda, WarpStream, BuffStream, they don't have that. So you have to spend more work to do these things. No reverse engineering, no guessing at undocumented semantics, and no playing catch-up. Our extension is scoped to the storage layer, the Kafka protocol handling, client interactions, and API surface remain the real thing. So I'll reread this. Our extension is scoped to the storage layer. So they're only on the hook for maintaining and evolving the storage layer, and the other stuff, the hard stuff as well, protocol handling authentication, handling client responses, and the API surface. I guess more things as well is difficult here, so that makes sense. This is not a one-off April Fool's experiment, they say. It's a high-conviction strategic bet. We're extending native Apache Kafka with a LakeStream foundation, and we plan to open source this work and invest in it for the long term. That's an interesting point. They call it a LakeStream. This is the first time I've seen this word, right? Lakehouse topic, or a lakehouse is something where you have an open table format like Iceberg, but LakeStream is, I guess, a stream that goes into a lake. A stream that goes into a lakehouse, I guess. So I guess they call LakeStream this thing where you have topics that go to lakehouse tables or to lakehouse. Sorry, I'm getting mixed up in the buzzwords myself. I guess they call LakeStream a topic which produces data and gets stored in an open table format like Apache Iceberg or Delta Lake. I guess that's what they call the LakeStream Foundation, which is cool. There were some people working on similar things. One of them was Ivan. Let's see which article I have here. So around this time, around May and July, Philip had a lot of very cool blog posts from the Ivan blog. They announced diskless Kafka back then, and then they talked about Apache Iceberg and Kafka as well. And they open sourced here something called Iceberg Topics, which was in the tiered storage KIP 405 in Kafka. They directly added some logic that, I don't know if I have anything highlighted here, but they added some logic where as Kafka would store the data in tiered storage, it would just store it directly into an Iceberg format and nothing else. And this is, again, they call it a zero copy path, because you're not copying the data, you're just writing it directly into an Iceberg columnar format. And then if you have a consumer read in the Kafka API, it reads off of that and converts it to Kafka and then gives it to a consumer. The benefits here mainly are, I think, the latency is lower, or the lag. You get the data in the Iceberg topic faster, and also you pay a lot less for storage because you don't have to pay for two storage copies, the Kafka copy and the Iceberg copy. You only pay for one. So they announced this. When was it? This was in July 2025. So almost a year ago now. This has been in the open source, the zero copy thing. Before that, there was Apache Kafka connector, Apache Iceberg connector that was also open source, and it still is. But yeah, these guys are also taking that step. And BuffStream also had this. BuffStream is another product that also had direct writes that go in a LakeStream format, I guess, a LakeStream topic or whatever. The writes in BuffStream would go directly to again, Apache Iceberg table, if I remember correctly, and the reads would also come from that Apache Iceberg table. And the other one that I also suppose is Tansu, one of my favorite open source projects as well, which also had somewhere here the ability to save stuff in open table formats, as it says here, automatic conversion of schema topics into Delta Lake, Iceberg, and Parquet file format. It's called a sync topic here in Tansu. So I guess so far we have 3 to 4 basically zero copy projects. There was also this, a few months ago, there were arguments on whether it should be zero copy or not. I think LakeStream published something where they bashed zero copy because their solution was not zero copy. I think both ways make sense. I don't think it's worth to spend too much time debating on which one is the right one, honestly. But I think we're seeing the whole streaming industry converge in the open table formats. And I guess these guys call it a LakeStream, which I like the name of. I think we can call it a LakeStream. I think that's cool. So let's see what they say more. What does it mean in practice? It's just Kafka with the potential for richer topic storage options. Your Kafka topics are simultaneously lakehouse tables because Ursa writes directly to Iceberg and Delta Lake and object storage without expensive SSDs, connectors, ETL, nor duplicate storage costs, as I just told you. They also have no cross-AZ replication costs because Ursa's leaderless architecture eliminates the single largest cost driver in cloud streaming. So again, as I said, this is probably a diskless topic where the Ursa engine directly writes to S3 here, and there's no replication between brokers, so therefore you do not pay the cross-AZ cost that your brokers would pay by replicating the data. You get for free from S3, so that's cool. They have no connectors to get data into your lakehouse because the data is already there. You produce your Kafka topic and you directly query it as an Iceberg table from Spark, Snowflake, or Databricks, or whatever else. And your Kafka clients work with zero changes because it is the literal Kafka code base. So literally, it's like as if your clients are connecting to Kafka, and they are because it is the same code base. Every client, every tool, every connector you use already just work. We didn't replace Kafka, we gave it a lakehouse foundation. UFK extends Kafka, it doesn't replace it. You don't have to go all in. You can move some topics to lakehouse native storage while keeping others on traditional disk-based storage in the same cluster. This is a really good point I'm going to touch on in a second. Support both cost-optimized topics that are lakehouse native, up to 95% cheaper, and latency-optimized topics that are disk-based, the regular classic topics that can offer single-digit milliseconds. You're basically supporting both topic profiles side by side inside the same cluster. Move topics between profiles as your needs evolve, roll out at your own pace, start with your highest volume, latency relaxed topics, with your biggest cost drivers, and expand when you're ready. No big bang migration required. That's a very important point. And there was only Ivan that offered this back in the day. I think Ivan was the one that came up with this idea in the first place. And that's why I have them saved here. I think this was the original announcement by them. Let's see what do we have here. So this is the original announcement when Ivan announced diskless Kafka, which was the project to take the diskless solution, which is write directly to S3 and don't replicate, and have no leaders and be scalable and a lot cheaper, and take it to the open source. And this was announced in April 2025. And the one thing they talked about here is the flexibility of just changing it with the topic option. Here's the example here, great example. You getting started with diskless topics is just one line. You upgrade your Kafka and then you run Kafka topics, create topic with a config type that's diskless. That's how there is. So you can see that even back here a year ago, they were parroting this idea of not having to fork your estate because solutions like Confluent Freight or WarpStream were like, hey, we have a diskless Kafka here. It's much cheaper, 10x cheaper, whatever marketing bullshit. And but if you want to use it, you have to create a new cluster and migrate your data or migrate your consumers, etc. Whereas these guys are saying, no, you should not have to create a new cluster and have separate clusters for your diskless workloads and have your classic Kafka cluster for your classical low latency workloads. No, it should all be supported in the same thing, in the same project. And I like that idea a lot. It comes with a little bit of trade-offs. Obviously, you don't get the full cost savings if you're not running everything diskless, and you don't get the full elasticity and auto-scalability if you're not completely stateless. But I think it's a good enough trade-off in not having to support two different systems. So this is what Ivan announced back in April, and I think they shipped it here or a month later. I have the other article saved. So here I guess they announced the idea of this. And then a month later, in a blog called Diskless Kafka is a Tide, and it's rising. I think they had really good blog posts back then. I think here they announced it. So I have some stuff saved. Let's see what I have saved. In May of 2025, they said Do you need sub 100 millisecond latency? Keep your topics on the hot replication path, meaning keep classic topics. If you want the rock bottom cost for your logs, telemetry, or backfill type of workloads, flip to diskless topics at the flip of a switch, as I said here. No other diskless solution lets you make that call per topic in a one cluster, one protocol with two different economic profiles. So these were the first guys to do it. And they did it again on top of Kafka, which they published in a temporary fork as well, which is still running, called Inkless. So this is the Inkless fork. You can see Claude cooking here with them as well. That's really cool. And the Inkless fork, again, took Kafka, forked it, and again, just added a separate storage path, I guess. Yeah, a separate storage path, a separate write and read path that wrote directly to S3. And that's a diskless path. And they said that they were doing this intentionally as a short-term fork. They say they don't want it as a long-term fork and they don't even accept patches. It's for informational purposes and they're actively contributing to the open source kit that's going to go to Apache Kafka. And I guess they're using this both as something to sell in the meanwhile and also something that's working and to basically help them inform the final open source solution they're going to ship. But I was really excited when this first came out because, again, it was a real differentiator between Ivan and all the other streaming products that did not have different topic profiles per cluster. They force you to create a new cluster. And here in this article, Philip again talked about some really cool stuff. One of them was the internal network effect of Kafka, where basically he's talking about the fact that having to fork Kafka became popular and became so used because of the internal network effect that the system has when you deploy it in an organization. Meaning, when you deploy Kafka in an organization, you start putting data into it. It goes so-called data gravity. It gets a lot of data in the system. And when you have the next use case, N+1, that use case asks, okay, where can I get, let's say, here he's giving an example with payments. And let's just read this. Picture day one. An ops team CDCs the payments table into a Kafka topic. On day one, a fraud detection service subscribes and starts flagging anomalies. On day two, finance spins up an audit log consumer that archives the same payment stream to cold storage. On day three, an intern asks, how do I trigger auto-scaling before payment traffic spikes? And the answer is a one-liner. Well, the payment topic already exists. Just read it and react off of it. And here they're saying that there's no extra ETL, no glue jobs, and no new security or ACL dances to be done. As you have more and more data in your Kafka topic or in your Kafka cluster, you're able to add more consumers, downstream clients and consumers on top of this, and that's what spins up the internal network effect, basically saying that that Kafka system, that Kafka cluster gets more and more valuable as time passes and as you put more stuff into it. And having diskless solutions that force you to fork your estate and say, no, create a new cluster, breaks that in half. It breaks that flywheel because suddenly, well, where is the payment topic? Okay, the payment topics is in the fast Kafka, but maybe the payment analytical topic is in the slow Kafka, in the diskless Kafka. So now you're not solving or you're not collecting everything in one place. You're breaking that network effect flywheel. And it forces people to separate where data is stored, and it forces consumers to separate, and you don't have the same incentive to use Kafka as you did before. And that's generally, I kind of butchered it, but this is what sort of I think Ivan was talking about here, or Philip actually. And the second thing that they talked about was the network effect, the second network effect, which was the external network effect. An external network effect here I define as, why is Kafka so popular? Why is everybody using the Kafka API? Why is the ecosystem so popular? And one of the reasons is that the more stuff we commit to Kafka, or the more innovation comes to the Kafka protocol. WarpStream separated the internal network effect by forcing you to have a separate cluster that doesn't support the same amount of stuff or the same amount of features like fast topics. It still brought something entirely new, which was the diskless topics. And that's the second network effect. The more stuff you add on top of the Kafka protocol by other solutions, the more people are incentivized to adopt Kafka for whatever it is. For slow topics, for fast topics, it doesn't really matter. So Kafka basically has two network effects. And the reason I highlighted this here actually is because it ties to the StreamNative announcement. When StreamNative says, hey, we're a Kafka company too, they're helping this external network effect of Kafka, because suddenly we have yet another solution that offers Kafka support or Kafka API support. You can use your same Kafka clients, you can use your same ecosystem on top of the StreamNative product. And it extends it with so-called LakeStream topics, or the ability to store topics in a zero-copy way in S3 on an Apache Iceberg format or Delta Lake format. And while this isn't brand new, like, as I said, Ivan kind of supported this, BuffStream kind of supported this. It's just another flavor with its own strengths and weaknesses, and that ultimately makes the Kafka protocol stronger. And as they said here, actually, Kafka is not just the system. You know, this is a competitor to Kafka, the system, but it's not a competitor to Kafka, the protocol. It's a friend to Kafka, the protocol. And that's how the ecosystem goes as well. And I think this was something worth highlighting here. I think we have everything we need from this blog post from Ivan. So I was just saying that Ivan were the first actually to get this flexible topic type thing out. And suddenly, or luckily, I think this was yesterday. Yeah, yesterday, RedPanda announced the same thing. RedPanda Streaming delivers industry's first adaptable streaming engine. I found this announcement really weird because they are not the industry's first adaptable streaming engine. It was Ivan, technically, that was the first one to offer an adaptable streaming engine to support both topic types. Now we're reading the Business Wire announcement here, which is probably not the best thing to read. We could probably read the other one, but let's get into it. Really shortly, I don't want to focus too much on this. They say one engine every workload. The latest RedPanda release configures different purpose-fit topics using a few distinct features. One is write caching, which is designed for ultra-low latency, providing an extreme speed boost for performance critical applications with in-memory caching. So think of this as like very fast topics. Then they have classic topics with tiered storage that straddle the cost-speed trade-off by spanning both local disks and cloud object storage. Tiered storage balances the performance and cost like a slider according to precise user preferences. This is more for storage reasons, but basically they still have classic topics, which are, let's say, tens of milliseconds of P99, end-to-end, maybe up to 100 milliseconds, maybe less. Write caching is something faster. I don't know the exact performance. And then they have cloud topics, which is their version of diskless topics. The cloud-first approach that writes message contents directly to object storage for extreme cost efficiency at massive scale, delivering over 90% savings and cost-AZ networking fees levied by some cloud providers. So they're adding these three types of topics, and also it seems like they're announcing Iceberg topics. That's a zero ETL approach that automatically materializes select topics into Apache Iceberg tables. I'm not too aware of this, haven't looked into it too much. And they say, unlike diskless Kafka alternatives that rely entirely on object storage, RedPanda lets users combine these powerful features at will, tailoring each workload in a shared cluster while retaining unique architectural advantages. Yada, 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 yada. Keeping it all in one cluster eliminates the reliance on the external control plane, as something like, let's say, WarpStream does this. Another focus for another day on VPCs and whether you control the whole system or your sort of split system like WarpStream, or whether it's a complete SaaS like Confluent Cloud and you don't control anything. But basically, I'm just opening this to show you that RedPanda is also announcing and just released apparently the ability to have multiple topic types in the same cluster. They're not the industry first, but they did do it. Again, I have it highlighted in red here. I don't agree with that. They had some extra wording here. It says, most vendors solve the problem of high-volume, latency-tolerant data by telling you to spin up a specialized diskless cluster. And that sounds fine until you're managing 3 different technologies, 3 different security models, and 3 different ways to do observability. And that's super true. That's super true. So nowadays, I think we have 3 solutions that offer something like this. We have Ivan's Inkless. We have StreamNative's UFK powered by Ursa, and we have RedPanda R1. In the future, we're going to have Apache Kafka, the open source thing, when Ivan finish shipping the kip, which might realistically take a year or 2 more. I wanted to focus also on WarpStream for half a second as we end out this video. Oh, actually, we should not end out this video. We have more to talk. We didn't finish the whole article by StreamNative. But while we're on the latency topic, WarpStream recently announced so-called lightning topics. And I didn't spend too much time looking into it because I was busy with other things at the time. But no, I want to see the blog post. But lightning topics was, held as this big solution that helped them reduce their topics massively. And they market it as that. Like everything in this blog, they always market something, usually something else behind. That's the actual truth. But just to give an example of where WarpStream is with regards to supporting different types of topics, because it can get confusing. WarpStream also supports low latency topics. The difference here is that they force you to deploy your whole cluster, or at least your whole agent, with low latency topics. And there's no way to have high latency topics, low cost topics, and low latency topics, high cost topics inside the same cluster, from what I understand. Just the way that everything here is mentioned, it seems like they don't allow you to. They call it low latency clusters, not low latency topic types. So they say WarpStream is tuned for maximum throughput and minimal costs by default, but you can tune it for much lower produce and end-to-end latency. And then they talk about the different approaches that they can take to minimize the latency. This is not actually the docs I was looking for entire. I think it was, I was looking for their Express docs. I think I might have it here. Let's go through the documentation a bit. I think this was the one, yeah. Yeah, exactly. So WarpStream has the ability to write data because it's made to write to S3 by default. It's usually high latency. It was designed for that. But then S3 Express came along that writes data to one zone, and WarpStream figured out a way to leverage that and offer low latency topics. Now, because S3 Express goes to a single zone, to have the same replication as Kafka, you need to write to a few zones. So they did something like a quorum write, where the agent takes the write and writes in parallel to multiple S3 Express zones. And when I think 2 out of 3 complete, they return a response to the client, something along those lines. And that does reduce the latency to some amount. I'll show you in a sec. But it also increases the cost. And here I was highlighting this because the way it's deployed, it seems to imply that your agent can only do one of the other. So you either start the agent with a bucket URL, which gives you the default S3 standard path that's slow and cheap, or you add these 2 different URLs, which deploys the S3 Express type of cluster, which lets you have faster latency, but at the same time it's higher cost. That's how I understand it. Again, I don't think the documentation is really good. It's not exactly clear. Can I have multiple agents with the same control plane and the same sort of cluster in terms of topics supported? I don't know, but it seems like no. And if they're not calling it out and if they're not marketing it, most likely the answer is no. But here you have they've done a really nice breakdown of all the features they support to lower latency. And the S3 Express lowers the latency by the most, so it reduces the produce latency and reduces the end-to-end latency. They say it increases cost by 20% on average, but I don't trust anything by WarpStream nowadays, so it's probably by 40-50% or whatever. But regardless, you can calculate this. It's a little difficult to calculate. But here, they have this example where if you're using regular WarpStream settings that are not tuned for latency, you can expect produce latency of 250 to 500 milliseconds and the end-to-end latency, which is actually what matters. End-to-end latency is defined as from the moment my producer writes something, when would the consumer read this. The P50 is 500 milliseconds, and the P99 is 900 milliseconds, call it a second. So from the moment you write something to the moment your consumer will read it, it will take around a second with the cheap tier. Potentially also higher than this, I guess, but I guess in the average it's around a second. Now, if you configure S3 Express and you reduce some of the batching, so you reduce the linger batching on the producer client and you reduce the batching on the agent itself, then you get somewhat better latencies, where the produce latency goes down almost 3x here from what they're showing, and the end-to-end latency goes down around 2x, which is what's actually important. So even the fast WarpStream here, let's make no mistake, even the fast WarpStream here is still slow. P50 of 200 milliseconds is very slow for end-to-end, and P99 of 400 milliseconds is, again, extremely slow for a fast Kafka. So they don't actually give you low latency, they give you, call it medium latency. And I think calling it low latency here is a little bit of a misnomer because, I mean, regular Kafka topics we could call it low latency. I'm not sure we should call it low latency, but regular Kafka topics are a P50 of, let's say, 50 milliseconds, depending on how well you configure it, and P99 of, let's say, 100 milliseconds, 150, with the ability to get that down a lot lower if you configure it more precisely and more carefully. So calling this low latency is bullshit. And then I want to call this out because I realized this recently. So then they released these so-called lightning topics using the lazy log paper, which is a very popular paper. Let's see if we can find it. I'm not going to go into any of this, but some complex stuff. Talking about the ability to decouple the durability and sequencing of Kafka messages. So sequencing here means when I write the data to S3, I need some centralized sequencing layer to give me an offset for that data, because the Kafka protocol requires you to have the offset of the record before you return. But that's only for the produce. So the limitation of the Kafka protocol is if I write a message with the producer, I expect the server to respond with the offset. And the difficulty here happens to be that if you want to have to call the control plane or have to call a centralized sequencing layer to give you a sequence, an offset for that message, and you want to store it in a durable way, both of these things add up to a lot of latency together, which is why the regular produce latency is P99 at 150 milliseconds. And the way they did here is they basically implemented some feature and they got the produce latency down by not returning offsets. So they're technically breaking the Kafka protocol and the Kafka API by not returning offsets. I think it was somewhere here, this call out. So caveats. Offsets returned from produce requests will always be 0. Applications cannot rely on the return offsets. And they claim that almost no applications rely on this, but it's good to be aware. I don't know if applications rely or not, but basically it's breaking the protocol. Another thing they had here is external consistency is no longer guaranteed. For example, if batch A is produced at time T0 and then successful acknowledgement is received at T1, and then the same producer produces batch B at T2, it is not guaranteed that it will show up in the log after batch A. The way I read this is they're breaking ordering. Like they're breaking ordering completely, and I don't know why it's mentioned as such a offhand thing, but that's how I read this. I mean, let me know if I'm wrong, but I'm very sure this is breaking ordering as well, which is a huge thing. And of course, transactions don't work, and idempotency doesn't work. So I feel like this barely works, honestly. It barely works, and the only thing it does, where people don't realize, is it only reduces your produce latency. It doesn't reduce your end-to-end latency. Look, the end-to-end latency here is the exact same as the X3 Express, which is what, if you've been in Kafka, you would know that what people care about, and the only thing people actually care about, is end-to-end latency. They care about the time the message was produced to a time it can be read, because the value, you don't get value by storing it in Kafka, you get the value from reading it from Kafka and actually building something with the message. So if you're doing a website end-to-end order flow of, let's say I'm ordering a mattress or something from a website and it has to go through Kafka, how fast that mattress gets ordered depends on the end-to-end latency. How fast can, let's say, the fulfillment service consume the order message from Kafka. So that's why the end-to-end latency matters. And the culture here is that they're marketing Lightning topics as something very fast. And if you don't understand these things, you read their marketing and say, wow, they're super fast. But it's actually not. This is very slow. 400 milliseconds is very slow. For a diskless Kafka, it's fast-ish, but it's still very slow for a regular Kafka, because a regular Kafka will do this in under 100 milliseconds, probably under 50 milliseconds. And I'm very sure RedPanda can probably get this down to under 25 milliseconds of P99 end-to-end latency. So I just wanted to call that out. Like, you can see their marketing here. Like, look at this little thing at the very top. I don't know if I can zoom in. Oh, it went away. But look at what it says. Lightning topics, producing to warp stream topics in under 35 milliseconds. Now, first, the 35 milliseconds is the P50. Is the P50. I don't think they mentioned it. Well, 33 here. The P50. Let me go back to this. The P50 is 35 milliseconds. So they're really just marketing the P50, which you never do with latency things. I mean, it's deceptive marketing, as simple as that. The P99 is still low, to be fair, so they could have used the 50, the P99, which is under 50 milliseconds, which is still low. But the key thing here is that this is producing and not reading, and reading is what matters. Again, look at this deceptive thing. This is talking about produce latency. They say a P99 of produce can be up to 700 milliseconds, which I think here they're showing 500 milliseconds. So is it 700 or 500? I don't know. And then they're showing the big example as if these topics are really that fast, but it's really just a produce, and it doesn't matter. So, that is deceptive marketing, as RedPanda basically always do. I don't trust this block at all, to be honest. Okay, rant aside, I just wanted to clear that out so you know that Ursa, that has classic Kafka topics, Ivan Inkless, which has classic Kafka replication topics, and RedPanda R1, which again has their classic RedPanda topics that all replicate to disk, is a lot faster than some of these other solutions. So even though WarpStream can say they have low latency topics, it's not low latency at all. It's not, I would call it medium latency because it's not even low by Kafka standards. And I wouldn't even call Kafka low latency to begin with. I would call RedPanda lower latency and low latency. But Kafka I would call just whatever, the Kafka latency. But anyway, again, just continuing. There's 3 products in the market right now that support flexible topics and lower latencies, like actually low latencies and diskless topics at the same time. Okay, well, so much to talk about. Do you understand how difficult this space is? Everybody's just talking their stuff. There's buzzwords everywhere, and there's so many different implementations that you get lost in the details. And you really have to think through things, and you really have to read through marketing very, very carefully. In fact, I wonder if I missed something here in the marketing. I hope I didn't, but let me know if I do, because I'm always trying to say how things are and go beyond just what the company is trying to make you think. So let's see what StreamNative is trying to make us think. We need to end this video. It's almost an hour again. So what about Pulsar? Well, fair question. If you followed us for any length of time, Pulsar is probably what you associate with StreamNative. That's true. That's what I associate with StreamNative. And here's the honest answer. Pulsar is not going anywhere. It's central to who we are. Pulsar continues to power the most mission-critical, business-impacting workloads for customers worldwide, yada yada. Organizations choose Pulsar for its multi-tenancy ability to handle both point-to-point queuing and ordered log streaming in a single platform, which I think Kafka does now too with the queue skip. It's decoupled architecture and it's battle-tested reliability. Those workloads continue to run and we continue to invest in them. But here's what Pulsar told us, and this is the part that matters most. The future of streaming isn't about which protocol wins, it's about what's underneath the protocol. And I agree with that 100%. I think that's a great quote. Again, the protocol has already won. Kafka has won, but the future of streaming is about who's going to give you the best engine behind the Kafka protocol. So that's how I would phrase this. Pulsar showed us that compute storage separation changes everything, that decoupling the broker from its storage unlocks a fundamentally different operational model, one where brokers are stateless, elastic, and cheap. We've been operating stateless, storage-separated streaming at scale for over 7 years through Pulsar, long before diskless Kafka became a trend. This is a nice jab to the diskless guys. I think it's a fair thing to call here because they really did have that separated architecture as soon as Pulsar was released, from what I understand. So they do have some experience in operating this. That operational experience is baked into every layer of Ursa and UFK. But Ursa taught us something else too, something even more powerful. When we built Ursa and moved streaming data directly into open lakehouse formats or open table formats, we discovered that lakehouse native storage doesn't just save money. It completely dissolves the boundary between streaming and analytics, unifying it all into a single queryable system. Ursa for Kafka UFK will show that any streaming protocol, even the world's most popular one, Kafka, can benefit from that foundation. Nice, that sounds good. Pulsar remains at the heart of StreamNative, is the foundation that taught us everything about cloud-native streaming, but we're not a Pulsar company. We're not a Kafka company either. There are no such companies anymore. What truly matters is what is behind the protocol. That's a great point. I love that. There is no Kafka company. There's no Kafka guy either. It's just what's behind the label. This point here is cool. It completely dissolves the boundary between streaming and analytics, unifying it into a single queryable system. I like how that sounds. You just write it to Kafka, and then you can query it from Snowflake automatically for free. We're seeing a convergence of technologies, or consolidation sort of, which is really cool. Deeper integration is something we can now benefit from. And they continue, and I guess we get close to ending here. Instead, we define ourselves as a LakeStream company. We ship a streaming meets lakehouse solution that now speaks both protocols natively. UFK is how we bring our LakeStream vision to the Kafka world. So I guess they call themselves a LakeStream company. Again, first time I'm hearing LakeStream. But I guess we call LakeStream this, which is merging the streaming boundary, the Kafka API layer, with open table formats, which indirectly merges it through queryable systems. And that's what a LakeStream company is, which if you think about it, it's not that different from what Confluent tried to do back in the day. Confluent tried to merge SQL with Kafka. When they released KSQL in 2018, 19, whatever it was, they were again trying to dissolve the boundary between streaming and analytics and let you query your streaming workloads through SQL in a native way. Now, they failed doing that, didn't catch on, and obviously today Iceberg and open table formats are catching on, and it seems like there will not be one querying engine that wins. But we see all the companies trying to continue fulfilling that vision by bridging Kafka and open table formats. So to really just be streaming APIs, which is the Kafka API, and the storage format, which is Iceberg or Delta Lake, and that's what the LakeStream is. Try it. UFK will be available as native Kafka service on StreamNative Cloud. It will enter limited public preview soon. They have 1,000 to give in credits on anyone who signs up, no strings attached. What you find is your existing Kafka clients work. Your Kafka topics are now also Iceberg and Delta Lake tables, queryable from yada yada, and your infrastructure bill is going to be a lot cheaper. If you use Pulsar, we're a Pulsar company. If you use Kafka, we're a Kafka company too. Come see what that means. And next week, we'll share more stories behind UFK. And that's it. That's everything I talk about today. So I like this announcement. I think it's a great development. It's a great development for Kafka and the Kafka ecosystem. We're getting more and more convergence into a Kafka protocol, and it certainly seems like the Kafka protocol is, you're probably going to keep seeing this logo, this Kafka logo over here for the next 10 years, honestly. Maybe not because you're using the project, maybe you're using the StreamNative logo as the project, but underneath it all, this is the logo of the streaming protocol. That seems like it has won, and it will continue winning. So I keep asking myself, how long until the next domino falls? How long until Databricks implements the Kafka API? How long until Redis streams moves to the Kafka API? How long until Snowflake introduces the Kafka API? We've already had our 3 cloud providers move to the Kafka API. So I think it's a matter of time for everybody else to follow. Thanks for watching.